Our universe, the galaxies, the solar system, our home planet Earth, land, sea, air, and life itself. Where did it all come from? If you look up into space from our planet, you'll see a vast cosmos teeming with billions of stars and galaxies. But turn back the clock 13 billion years, and our universe was so small it could fit inside the palm of your hand. From this infant universe, everything would be created. The stars, the galaxies, and the building blocks of life itself. The calcium in our bones, the iron in our blood, the atoms for the air we breathe, the water we drink, and the raw materials for building our cities and machines. We're about to take a journey through space and time to discover how the universe was born, how it created everything in our world today, and how eventually made of matter, atoms and molecules. This 1956 Ford Fairlane convertible is constructed from many different materials, including steel, rubber, and glass. These materials are made up of combinations of elements like iron, silicon, chromium, and carbon. And each and every atom that makes up those elements was created by our growing universe. Physicist Lawrence Krauss studies how the atoms we find on our planet today came to be here.
We really are part stardust and part Big Bang dust. Most of the atoms in our body are from the cores of stars, but some of them have been around since the earliest moments of the Big Bang. So we really are truly cosmic individuals.
Each and every atom was created over billions of years as our universe evolved.
So when we look at this car, of course, all the atoms in this car came from stellar explosions, from supernova processes, and from stellar evolution. But they were created at different times during the evolution of the universe.
To understand how the universe made the raw materials on Earth today, we're about to take an incredible journey and travel back to the moment our universe was born. In the beginning, there was nothing, no space and no time. Then there was light. Suddenly, a tiny speck of light appeared. It was infinitely hot, and inside this tiny fireball was all of space. This was the beginning of time. The cosmic clock then began to tick. Time could now flow, and space could expand.
At the earliest moments of the Big Bang, if you take it back to t = 0, everything in our universe, everything we can see, all the matter and all the energy in all of the galaxies was once contained in a region smaller than the size of a single atom today.
The idea that our universe was once tiny came from the brilliant work of American astronomer Edwin Hubble. Back in the 1920s, most astronomers believed that anything visible in the night sky was a star, and that all stars were part of our galaxy, the Milky Way. But Hubble wasn't convinced. He began to study a swirling cloud of lights called the Andromeda Nebula, and eventually showed that it was a star city, another galaxy far outside our own. He also showed that other galaxies were speeding away from ours, and the further away they were, the faster they seemed to be moving. The universe was therefore expanding. And if this were the case, then at some point in the past it must have been much smaller. And it must have had a beginning. The idea of the Big Bang was born. Theoretical physicist David Spergel is a Big Bang expert.
The Big Bang theory is not really a theory of how the universe began. It's really a theory of how the universe evolved.
No one knows exactly what happened during the Big Bang, but scientists do know that just a fraction of a second after the universe was born, this tiny superhot fireball had already started to expand.
We don't know how the universe began. So we start our story when the universe was a billionth of a billionth of a billionth of a billionth of a minute old. Pretty young. The universe was the size of a marble.
Less than a trillionth of a second after the Big Bang, the marble-sized universe was very unstable and underwent an enormous growth spurt.
During this period of incredibly rapid expansion, space itself was expanding faster than the speed of light.
In the same way that this hot glass ball inflates, so did the baby universe, expanding in all directions at once. And as it expanded, it cooled. Immediately after the Big Bang, the universe was small enough to fit inside the palm of your hand. A tiny fraction of a second later, it was the size of Mars. Another fraction of a second, and it had grown to 80 times the size of the Earth. And our newborn universe continued to grow. But at this stage, it didn't contain matter. It was pure energy. Einstein's famous equation, E equals mc squared, demonstrated that mass and energy are interchangeable. It provided us with the knowledge necessary to build nuclear weapons, and it also revealed how the universe created the first matter. When a nuclear bomb explodes, a tiny amount of matter is annihilated and converted into energy. In the baby universe, the exact opposite happened. It converted pure energy into particles of matter. But there was a problem. The universe created both matter and its arch-rival, antimatter. And when these two met, they obliterated each other. The infant universe was a war zone. If matter and antimatter had completely annihilated one another, the universe would have remained full of energy, with no galaxies, stars, planets, or life. But fortunately for us, there was an imbalance. For every 100 million antimatter particles formed, there were 100,000,001 particles of matter.
But there was that one extra particle of matter left over in each volume. And that was enough to account for everything we see in the universe today.
This tiny imbalance led to the formation of all the matter in the universe. Galaxies, stars, planets, even convertibles and ourselves. Astrophysicist Carlos Frank from Durham University explains.
We are a little bit of debris left over from the annihilation of matter and antimatter. We're the leftovers of that process. If the universe had not developed this slight asymmetry between matter and antimatter, the universe would have been completely boring. There would be no structure, there would be no galaxies, there would be no planets.
What this newborn universe was like is a question that has challenged cosmologists ever since the Big Bang theory was first proposed. But now, in one of the biggest laboratories on Earth, scientists are able to recreate the conditions that almost certainly existed a mere instant after. Scientists like Todd Satogata accelerate subatomic particles close to the speed of light and then smash them into each other. The particles race around a 4-kilometer-long circular tunnel.
What the very early universe was like.
When the particles collide, they break open and throw out a shower of even smaller particles. The process is a bit like discovering what cars are made of by watching them crash into each other.
You can race two cars together and smash them into each other head on. And when you do that multiple times, you start to see different patterns coming out. A tire comes out here, a radiator comes out there, and before long you can start to conclude that a race car is made up of these certain pieces.
Scientists at Brookhaven have discovered that within these superheated collisions, a completely new form of matter appears. And this matter contradicts the previous theories about the nature of the early universe. Because it's not a gas, it's a liquid. This liquid was super hot, 100 million times hotter than the surface of the sun. And the vast quantity of energy inside the young universe caused its particles